Now from the syllabus itself, it is very much clear that we have to conduct the programming in either C++, Java, Python, okay, as per your choice. But most of the people, I think personally, they'll be compatible with Python. So you can take any of these languages for the programming part. Then as far as the syllabus is concerned, it is very much clear that we have to conduct any 5 assignments from group A and one mini project is to be conducted. So there are total 6 assignments given here. Out of these 6 assignments, 5 assignments are to be covered, and out of 4 given mini projects, one mini project is to be completed, right? So this is as far as the syllabus is concerned. Now moving on towards actual assignments. So I'll be taking the first 3 assignments as I told you, like I'll be discussing these 3. First assignment is write a program, non-recursive and recursive program to calculate Fibonacci numbers and analyze the time and space complexity. Dear friends, as Parikshit sir correctly said that writing a program is not a big deal as of now, right? What students need to understand is the basic concept behind that particular algorithm. So personally, I feel that we need to make the students understand the algorithm first. Then as this statement says, we need to analyze the time and space complexity of the algorithm. So first I'll be talking about the algorithm, then we'll calculate the complexity, and then we'll move on to the program. Okay. So to begin with, here is the algorithm. Now you can see I'm passing an integer, a parameter, and if n is less than equal to 1, then we are writing n as it is. Otherwise, we are moving on. This is I'm talking about the iterative version, right? So else, I'm not going to explain that algorithm, what exactly it is. So I've taken 2 parameters, sorry, 2 variables. F and m2 is equal to 0 and f and m1 is equal to 1. And then the loop runs. Okay. Now, if you talk about the complexity of this particular algorithm, you can see there are 2 parts. One is if the condition is true and if the condition is false. Now what happens if the condition is true? That means if value of n is less than or equal to 1, what happens? Here condition will be checked and this write statement will be executed. Okay, you can see there are this condition 1 and this write statement 1. So there will be total 2 statements executed. Now, while discussing the complexity, we need to, students are expected to be aware of something called as steps per execution. And second one is the frequency. What are the steps per execution? They have already studied, but probably we may need to revise these things here. Steps per execution is what? Like whenever I'm writing a statement like c is equal to x plus y. Now, when this statement is being executed, inside this, how many statements are involved? Okay, that is steps per execution. It is very well explained in Fundamentals of Computer Algorithms by Ilis Horowitz-Sani. Okay, you can refer that book. Here in this case, the steps per execution will be equal to 1. Another example, suppose I'm having c is equal to sum of x comma y. And if I go to the definition of sum x comma y, I will not write the correct syntax in detail like this. Okay, now if you go to this particular statement, what happens? This statement needs to be executed. But when this statement is to be executed, as we know that the control goes to the definition of this sum, right? So in the definition, let's assume there are 3 executable statements and here 1 statement. Now for this particular statement, when this statement is executed once, actually there are 4 statements executed. So here steps per execution will be equal to 4. Right? So we need to explain the students what do you mean by steps per execution. This is the one thing. Second thing what we require is the frequency. Now frequency is typically whenever you are writing certain statement inside a loop. So you just check out how many times that loop gets executed. So that is typically the frequency. Now whenever you want to calculate the step count of any statement, actually the steps per execution should be multiplied by the frequency if it is inside the loop. Otherwise it will be plain steps per count. Now coming back to what our discussion was, if n is less than equal to 1, then write n. So regardless whatever the condition is there, if n is less than equal to 1 or n is greater than 1, regardless that this condition must be executed. So I'm counting this step count as 1 and write n. If condition is true, that has to be executed once. So it is 2. Right? So if I'm talking about the time t of n is equal to 2, if n is less than equal to 1. Right? Now, if condition is not true, what will happen next? Now, the control comes into the else part. In else part, what happens is this line gets executed, right? And the loop you can see here, this loop actually gets executed n minus 2 times, right? And this also gets executed n minus 2 times. But this loop gets executed additional 1 time. Why? Because whenever this loop is false, value of I is equal to n plus 1. Right? At that time, this loop, the condition has to be checked. So that is additional 1. And in that case, the body of the loop will not be executed because body of the loop gets executed whenever the condition is true, right? So we are executing this additional 1 when our condition is false. And this will get executed once when condition is, false as far as the n value of n is concerned. So if you calculate the count, it will be 1. This will be n minus 1. This will be n minus 2. This is plus 1, which roughly comes out to be, sorry, this is n minus 2, but there are two statements. So this is into 2. So it will come out, I'll write separately, n minus 2 here, n minus 2 here. So it comes out to be n minus 1 plus n minus 2 plus n minus 2 plus 1. And as there are two statements, you can see there are total 2 initialization statements. So I'll be writing it 2. Right? So it comes out to be and one more thing here also, if you observe here, there are also two statements, right? Two assignment statements. So I'll need to write plus 1 n minus 2. So let me write it little properly. I'll just remove the whole stuff. There are this one plus this one. This will be total n minus 1. This is n minus 2. You can see there is one assignment statement which will get executed n minus 1, n minus 2 times. This assignment statement gets executed n minus 2 times, right? And this is plus 1 time. Now, if you perform addition of all these, that is 2, 1 plus 1 plus n minus 1 plus n minus 2 plus n minus 2 plus n minus 2 plus 1. Okay, this is when our condition is false, but we are missing one thing. That is when condition is false, as I said earlier, regardless the condition that gets executed, that means it will be plus 1. So I need to write this plus 1, which comes out to be 4n. I'm calculating this sense. So it comes out to be 4n. And this will come out to be 1 plus 1, 1, which comes out to be minus 1. Okay, 4n minus 1, if you can check it out. N minus 2, n minus 2, n minus 2. Okay. And minus 3, I guess. 4n minus 3, right? Now, this is the complexity of the Fibonacci. Here we have to explain how the complexity is to be calculated. So I have explained about the steps per execution, then frequency, and then we speak about this. So what are steps? I have spoken about these steps are very well covered in fundamentals of computer algorithms by Horowitz. Right? Then comes is the algorithm. So all these steps are given here. Then comes out to the program. Now here we are talking about the program. I'm not going to explain the Python program because once you have understood the iterative algorithm, I don't think there is any difficulty in understanding the program. What is our intention is to understand the algorithm. So this is about the program. Then moving over to the recursive algorithm. Now in recursion, we can see again same algorithm. So Fibonacci n, I'm passing parameters, then comes out to be n is less than equal to 1. So we say return 1 and else Fibonacci n minus 1 plus R Fibonacci n minus 2. I have written R to just indicate it is recursive version, nothing else. Now if you talk about the complexity of this, Okay, so what I'll be doing here is I'll be calculating T of n. Okay, T of n we need to calculate the T of n. As we said in earlier case, T of n is equal to 1 if n is less than equal to 1. Now we need to talk about what happens otherwise. Now if you look into this, this is a recursive version, right? This is a recursive version. So let's concentrate on this part, which comes out to be T of n is equal to T of n minus 1 for this recursion. How much time I'll take? So it will be T of n minus 1 plus for this it will be T of n minus 2 plus some constant value, right? Now you can see there is a recurrence in this equation. Now, as all of you know that we need to remove the recurrence. In DA also we spoke about like it is expected that we should remove the recurrence. We can use any of two methods, either the substitution method or the master theorem. Here I'm using the substitution method. So what I'm doing is now this n of T of n minus 2 by the approximation I'm writing it as T of n minus 1. So it is approximately equal. And this equation can be rewritten as 2 into T of n minus 1 plus C constant as it is. So I get this equation and this recurrence I need to remove. Here I have used a method of substitution. I'll just keep on substituting T of n minus 1. Then it will be further written as 2 into T of n minus 2 plus C. So this is the replacement for T of n minus 1. So keep on substituting like this. So here I can get 2 into 2, that is 4 T of n minus 2 plus 3C. Now keep on substituting. Next step, I'll get into something called as 8T of n minus 3 plus 7C. Now if I generalize this particular statement, I get, if you write this 8 as 2 to the power 3, okay? So I'll be writing it 2 to the power k. 3, I'm going to generalize it. So 2 to the power k multiplied by n minus, here 2 to the power 3. So 3 means k. So I'll be writing instead of 3, I'll be writing it as a k. So it comes out to be T of n minus k plus this is 7, right? The 7, how can I write it as 8 minus 7? How can I write 7? 2 to the power 3. That is 2 to the power k minus 1 multiplied by c, right? So I'll get this equation. Now I can substitute this k, or I can have this equation n minus k is equal to 0. That means I can get k is equal to when I'll further generalize it to write into T of n is equal to 2 to the power n multiplied by T of n minus k, right? So k is equal to n, which gives me T of 0 plus 2 to the power k minus 1 multiplied by c. Now what is 2 to the power, sorry, what is T to the power T of 0? We have also written earlier. Whenever value of n is less than equal to 1, I should write it as 1. So this gives me n into 1 plus 2 to the power n minus 1 multiplied by c, right? So if I further write it, it will be 2 to the power n plus 2 to the power n multiplied by c minus c. Okay, now, so what I'll do here is from this equation, it is simple mathematics, 2 to the power n into 1 plus c. I'll take 2 to the power n as a common. So it gives me 1 plus c minus c as it is. Now, after ignoring the constants, I'll get 2 to the power n as a final answer. That means the complexity of the recursive algorithm, which gives me 2 to the power n, so T of n is equal to 2 to the power n, that is exponential. Now here we should be able to tell the students the very big difference between iterative and recursive algorithms. Why you should not prefer, or why should you prefer iterative algorithm over the recursive algorithm? Apart from their storage limitations, we should speak in terms of the complexity as well. There we have seen it comes out to be, if you write in terms of upstream protein notations, as far as the iterative algorithm is concerned, the complexity was big of n, whereas in case of recursive, it comes out to the we go of 2 to the power n. Right? So here is a huge difference between these two complexities, and then we should tell us which algorithm is to be preferred and why. This is how we can explain the recursive version of Fibonacci series. Again, here is simple algorithm in Python, the recursive program for the, here I have written factorial, but it is Fibonacci. Then comes is the Huffman coding, right? Now here we have to use the greedy approach. Now in greedy approach, there are certain requirements as far as the Huffman coding is concerned. Hopefully we are explaining what is Huffman code, right? All those things will be explaining the frequencies, then messages. We need to explain all of them. But when you're talking about Huffman coding, it is two-way merge technique, right? The basic requirement is that whatever frequencies are given, these frequencies are to be in sorted order. So I have taken an example of 7 messages A to G, and these are the respective frequencies like 4, 7, 12, and so on. Now what I'll do is I'll be merging two minimum frequencies. So first I'll merge 4 and 7 to get into 11, right? Smaller node on the left hand side, larger node on the right hand side. Then whatever frequencies I remain, 11 is my new node now. So I'll be taking again all these nodes, arrange them in ascending order, and then merge two minimum nodes. So in this example, you can again have 11 and 12 to be merged. So I'll create a new node called as 23 after merging 11 and 12. 11 on the left hand side smaller, bigger element on the right hand side, right? Again, whatever these remaining elements are there, I need these elements to be sorted, which gives me something like this. Okay. Now out of this, I'll be merging 14 and 17, right? So it gives me 31. 14 smaller on the left hand side, 17 larger on the right hand side. Then after merging these, again, whatever frequencies I remain with, I'll be sorting them in ascending order. Now you can see 23 and 31 are smaller. I'll merge them to get into 54. So it gives me 54. So I'll merge them together. Then 43, 52 and 54. Then for the two smaller frequencies, 43 and 52, I'll be merging them together to get into 95. So remaining two frequencies, 54 and 95 to be merged finally, which gives me 149. So this is how I get into. So once I complete this Huffman tree, with the assumption that left hand side will be denoted as 0 and right hand side to be denoted as 1, which gives me something like this, right? Now, once I'm done with this Huffman coding, Huffman tree, then I'll come to the leaf nodes, which are representing the messages. And starting from the root node to leaf node, I'll write down the code. So for example, if you talk about first message, that is A, I'll follow this particular line, right? Starting from the root node to leaf node, that is A, I get a code of 0, 0, 0, 0. So this is my frequency of A, and this is code of A. Same thing for B also we can see. Then C I have shown here. We can see D, then you can see E, F, and G, right? Now what happens here is if you look into these particular codes properly, here it is. The frequency of this was, let's say frequency for A was 4 and frequency for G is 52. Okay. The message which has got minimum frequency, its code is larger as compared to the message whose frequency is higher, right? This is what we have to explain. Just a minute. Okay, So we have to explain them how the Huffman code works, right? What exactly Huffman code is there, and then how it is to be calculated. Once they understand this concept, I don't think there is any difficulty in understanding the program as far as the implementation is concerned. So what we have done here is, here I have taken the frequencies, the messages in their respective frequencies. Same example I have taken in the program also. And then we have sorted them here. And then as we know that they are in sorted order, I'll be always picking up first two nodes and I'll be merging them together. And finally, I'll be printing the node. Right? This is how the Huffman code works. Friends, I'm purposely not explaining in detail the algorithm, right? Because this is specifically in Python. Some of you might want in some other language, as I said earlier, so that might be a bit different. This is the output I have shown here for the same program. Coming to the third part of the third assignment, that is fractional and abstract problem by using greedy approach. Now, we have to explain. Actually, it is expected to be explained in the subject itself. What is fractional and abstract problem, right? And then what are the various strategies they have followed and which strategy has been finalized. So there are four strategies actually, kind of trial and error they have taken. First is brute force. Second is we are implementing a strategy of something called as increasing order of weights. Okay. Third strategy is decreasing order of profits. And fourth strategy is decreasing order of profit to weight ratio, right? So these are the four strategies, but as it might be proved in the theory part that this particular strategy gives the optimal solution. So all these four strategies will give us the feasible solutions. Out of that, the last strategy will give us the optimal solution. So we'll be implementing the last strategy, right? Here, this algorithm assumes that whatever weights or whatever objects are there, these objects are arranged in decreasing order of their profit to weight ratios, right? Because the second and third strategy, that is increasing order of weights and decreasing order of profits, they are having their own limitations. For example, if you're talking about increasing order of weights, suddenly the remaining capacity of the knapsack decreases. Same thing happens in the third strategy, that is decreasing order of profits. The remaining capacity of the knapsack decreases drastically, right? And that's why fourth strategy will help us to give the optimal solution. So we have to explain the fourth strategy by taking an example. Here is an algorithm which I have taken it again from the Horvitz-Sani. The prerequisite for this algorithm, it says that whatever P and W we are going to consider, P is array of profits and W is array of weights. So some books, they say instead of profits, they call it as a value. Okay, value and weights, fine. So whatever objects are there, these objects are to be ordered in decreasing order of their profit to weight ratio. This is the prerequisite as far as this algorithm is concerned. Now what we are assuming is that whatever the solution vector is there, this solution vector will be initialized to 0. That means I have not picked up any object as of now. So my first loop says that for I is equal to 1 to n, do x of I is equal to 0.0. Make it clear that this solution vector is going to give us the fractional values as well. And that's why it should be 0.0, floating point number. So solution vector will be initialized to 0. Then what I'll be doing is I'll be picking up an object to the full of its capacity. That means I'm trying to pick up the complete object. So the solution vector for that is going to be 1. Before that, whatever m is there, I forgot to mention these two parameters. M is the capacity of the knapsack and n is the total number of objects. Okay, P is array of profits, W is array of weights, right? So these are the four things which you are going to consider. Now what I'm doing is I'm going to store this M, the capacity of knapsack, into a variable called as U. Right? Now here the strategy says that if you remember that strategy, we'll be picking up the first object as far as possible, right? So maximum in the sense that I'll try to pick up that object completely, 1. So solution vector will be 1 for that. Let's go ahead. For I is equal to 1 to n, all I'll be iterating through all the objects. If W of I is greater than U, what does it mean? Whenever I'm talking about W of I, so first object I'm talking about, the weight of the first object is greater than capacity of the knapsack. That means the first object itself, if value of I is equal to 1, I'm not able to place the first object itself into the knapsack. So I need to break it. If you're talking about the subsequent objects, that means value of I is 2, 3 onwards, right? So you are having that object and the remaining capacity of the knapsack is smaller than the weight of the object. So I need to break. So I'll be taking that object partially. How it is to be taken care of, that we'll discuss shortly. Now here, assuming that first object I can place it into. So condition will be false. I'll enter into the next part, that is x of I is equal to 1. It indicates that x of I means, let's say first, I'll be saying that first object is placed completely. Right? So x of I is equal to 1. I have placed it. I need to update the capacity of the knapsack because I have placed the first object. So remaining capacity of the knapsack is equal to U minus W of I. What is the W of I? Weight of the respective object. Weight of the respective object. So I'll be writing U is equal to U minus 1, where U indicates that it is the remaining capacity of the knapsack. Okay. Then if I'm assuming that I have placed the first object completely, I'll update this capacity of the knapsack. I'll move ahead. I'll check it. What is the capacity of the knapsack? U. Next weight, W of 2, let's say. Is W of 2 greater than remaining capacity of the knapsack? If yes, break, come out of the loop. If not, then x of 2 is equal to 1. That means I can say that I'll be able to place the second object completely. So x of 2 is equal to 2. Right? So this loop will check, can I place the object completely? Right? If yes, so I'll be having corresponding x to be equal to 1. If not, then I'll come out of the loop. So this loop is broken. I'll come out of the loop. Now I'll come out of the loop. I'll check a condition. Why I have come out of the loop? Is it that value of I is less than equal to n? That means still there are some objects which I have not taken care of because their weight is exceeding the remaining capacity of the knapsack. Right? So I is less than equal to n. That particular object I was not able to place completely in the knapsack. That means I need to take the fraction of that object. And that's why I can calculate x of I is equal to remaining capacity of the knapsack divided by weight of that particular object. So that much fraction I can place into the knapsack. Now for rest of the objects, it will be 0. Why? Because we have already initialized solution vector to 0. So for the rest of the object, there will be no change. It will be 0 as it is. Okay. So this is how we need to explain what exactly the greedy knapsack algorithm is. But again, I need to repeat it that we have to tell them whatever objects we are considering, these objects are considered in descending order of their profit to weight ratios. Here is the implementation. And here I would like to take an example here. What we have done is enter the values of 3 atoms. So these are the profits. We have taken 3 profits like 24, 15 and 25. Then comes out their weights. So I'll write down these profits. Weights are like 15, 10 and 80. Okay. Obviously n is equal to 3 and m is equal to taken as 20. Capacity of the knapsack has been taken as 20. Okay. So if I calculate profit to weight ratios, it will give me something like this. For this, it is 1.6, it is 1.5. And for the last one, 25 and 15, it comes out to be roughly 1.4. Right? So I have already arranged these objects in descending order of the profits. Okay? Now, I'll be writing x of 0, 1 and 2. It is initialized to 0, typically 0.0. If I take capacity of the knapsack is 20 and weight is 50. I can place the complete object, right? So I'll be writing down, I'll write down here u is equal to 20. So x of 0 is equal to, I have placed that object completely. Then value of u gets updated 20 minus the weight, that is 15, which comes out to be 5. Okay. Then is the second object. You can see the remaining capacity of the knapsack is 5, while the weight of that object is 10. I cannot place the complete object. So I'll break that loop and I'll come I is less than n, I is equal to 2, n is 3. So my loop is, condition is true. But it says that remaining capacity of the knapsack divided by W of I, weight of that corresponding object, which is 5.5 divided by 2, which comes up to be 0.5. So I'll be writing it down 0.5. Then what about the remaining capacity of the knapsack? This 5, okay, will be updated to get into 0, right? Now, so I'll not remaining capacity of the knapsack is 0. I'll come out of the algorithm and x of 3 still remains 0. So my final answer will be 1.5 and 0. So this is my final answer, 1.5 and 0. This is the solution. Here we have to explain, and we can, if we calculate the profit, it gives us 31.5. How can, so we can explain here, it is 24 plus, how 24? 24 multiplied by solution vector plus 15 multiplied by solution vector, that is 0.5. And for the last, we have not considered because solution vector is 0. If you calculate 24 plus 15, it will come out 7.5, which is 31.5. So this is the optimum solution, which gives us the maximum profit out of these 4 strategies. This is how we have to explain how the knapsack algorithm works, and then it will be easy for them to write program. Yeah, that's all from my side. I have referred this book, as I said, Fundamentals of Computer Algorithms. Whatever 3 assignments I have explained, they are given very well in this particular book. With this, I'll stop here. Before having any doubts, I can take those doubts.
Thank you very much, sir. Participants, any doubt till this session?
Good morning, all. Sir, I want to ask one thing. Hello, am I audible, sir?
Yes, madam. Yes, madam.
So second assignment is on Huffman coding using the greedy method. So, and in theory, Huffman coding is not given. So shall we take that particular method in theory or not? That point I want to make clear.
Madam, even though it is not part of your regular theory, but it is required for the practicals, right? Now, if you are the same teacher for theory as well as practical, you can cover it in theory and then it will automatically be covered in the practicals. But if there are 2 different teachers for theory and practical, because in some cases it might be different. So it is responsibility of the teacher who is conducting that practical to make the students understand this Huffman coding. If it is not covered in the theory part, because it is not part of our syllabus as such in the theory part.
So in theory, we are not supposed to cover that Huffman coding.
If time permits, you can, madam. If time permits, because as per my knowledge, I don't think you will be having sufficient time to complete that part.
Yes, exactly. That's my concern.
Yes. If time permits, you can go ahead with that. But it becomes little difficult for the students to, even though some concepts are already covered, still students get difficult to understand these complexities and all those parts.
Okay. Thank you, sir. Thank you.
Hello, sir.
Yes,
yeah.
Good morning, sir. In first calculating the time complexity, you have taken n minus k is equal to 0. Why it is n minus k is equal to 0? You have taken. This is my first question, sir. Second question: if you are recommending that we should ask students to go with the iterative algorithms rather than recursive algorithms, because the time complexity is big of n and 2 raised to n, right? But in case, let us say, if you are using while loop and we don't know how many iterations there will be in the program, then how we are going to calculate the time complexity in that case?
So just a minute. Your question was, can you repeat it?
While calculating the time complexity, n minus k, sir, you have shown in the slide, n minus k is equal to 0. So why it is 0? And second question is, uh, we are recommending iterative algorithms or recursive algorithms due to the
Okay.
time complexity. So if the while loop is there, if we are using in a program where we don't know how many number of iterations the program is going to perform, how we are going to calculate the time complexity in that case.
Okay. First of all, where I have written n minus k is equal to 0, actually it is an assumption to say that n is equal to k. That is an assumption, because in some cases we take n is equal to 2 to the power k. In some cases we take n is equal to k. That is an assumption. Okay.
Okay, sir.
First. Second thing, I'm not recommending to use iterative algorithm or recursive algorithm. See, what happens is that we should know, or we should explain the students what are the limitations of recursive. Remember, whenever you're talking about while talking about the time complexity as well as the space complexity, I hope you are aware of the space complexity, right? Space complexity is divided into three parts. One is instruction space, then recursion stack space, and data space. Now, when recursion comes into picture, we'll be talking about the recursion stack space. What does it mean? If you are having recursion in your algorithm, your whatever that PSW, which we call it as program status word, that needs to be stored, right? When you come back, when you return, that needs to be loaded. So I need to spend extra time on this load and store instructions. This is the basic limitation of recursion. First point. That means as far as the time is concerned, it will take time, right? Space, it will take space, because here you are having additional stack. Now, while talking about recursion and iteration, you can see there is huge difference between the complexity, between the time complexities, to be specific. It was big of n, and here it is exponential. And you know the limitation of exponential, as the value of n goes higher, then it becomes very difficult to solve that particular problem. This is the limitation of the exponential algorithm, right? So we have to explain the difference between recursive algorithm and iterative algorithm. So because of this more requirement of time and space complexity, recursive algorithms are not preferred. Coming to your third question, how to calculate our, how we'll know the number of iterations while talking about number of iterations in case of while loop, right? General formula says that your maximum limit minus lower limit plus 1. Use any loop, you have to use this formula. I repeat, maximum limit minus lower limit or minimum limit. Like let's say your algorithm is using for loop. It is for I is equal to 2 to n. So it will be n minus 2 plus 1. Let me finish. Let me finish. So if you are using while loop, in while loop also you have to have the initialization part, right? Earlier, before the while loop, you might have used I is equal to 2, and then in condition you are using something I is less than equal to 10 or so, right? In that case also it gives you the upper limit. You are already having the lower limit, so you can calculate the number of iterations in that case also. Yeah, please go ahead, sir.
Upper limit we have to assume, sir, here.
No, it is given. You are having the condition. No, in for loop, what do you say? For I is equal to 2, I less than equal to let's say 10, and I plus plus. So I is less than equal to 10. The 10 is the upper limit. In while loop also, what you have done is I is equal to 2 while I is less than equal to 10. So whatever condition you are adding in the while loop, that is the upper limit. You need not assume, it is given in the loop itself. You have to give it, because when your loop will be stopped, you have to give the condition, no? So whatever the maximum limit you have given to stop that loop is the upper limit. I hope I have answered your question.
Sir, there is one question in chat box from Professor Manjusha Madam. Sir, for mini project, what will be the team size? Either 2 students or 3 students?
I think that will be covered by Vaishali Madam, coordinator. I think she can tell it. I think typically 2 to 3 will be sufficient.
Can have. Yes,
Yeah, madam?
Yes, yes, sir. 2 or 3
Yeah.
you can have.
Yes,
Not more
2 to
than
3.
3.
Yeah, not more than 3, because we are talking about the mini project, so it should not go beyond 2 to 3. 2 to 3 is typically okay.
Okay, thank you, sir. So on behalf of Maratha Vidya Prasad Samstha Nasik, Board of Studies, Department of Computer Engineering, Savitribai Phule Pune University, Pune, organizing committee, and all the participants. I extend a very hearty vote of thanks to the respected Dr. Santosh Kumar Chobe sir, who spare his valuable time from his busy schedule and giving us all valuable information, guidelines for conducting the design and analysis algorithms practicals. So we thank you, sir, for being with us, and it has been a great pleasure, sir. Thank you very much, sir.
Yeah, thank you very much, organizers, for giving me an opportunity to interact with faculty members. And thank you all faculty members, all the participants for patient listening. Thank you all.
Thank you, sir. So with this, I request Professor Manisha Thumbre, madam, to introduce second resource person, Dr. Vaishali Tidki, madam. Yes, madam, over to you.
Madam, you are not audible.
Madam, you should unmute.
Just yeah.
Should I proceed, sir?
Sir, ma'am, wait, madam. Ma'am, wait.
Okay,
Ma'am, just
okay,
wait.
okay. Okay.
आता लगेच
Okay, meanwhile, are my slides visible, sir?
चालू होते की नाही असेल त्याच्यावर सिल्वर कलर हा
Yes. Golab, sir?
दीपला तर टाकू दे काय घ्यायचंय कशाबद्दल आहे काय मीटिंग
Yes, Chetty, madam, your slide is visible now.
Okay, slides are visible.
Yes, madam. No issue.
Okay, okay.
पेपर खाय थोडे खाऊ का आलं कुठं 11 वाजता जेवायचं
Yes, remaining participants are requested to mute themselves. Other than organizers, remaining
गेले काय
participants are requested to mute themselves.
केवढं जोरात मारलंय बसला काय वर आलंय का व्हॉट्सअप नाही बघितलं मीटिंग नाही अटेंड करायची कुणाची मीटिंग आहे काय म्हणत होते तुम्ही आता फोन आलता होय बोल
Swati madam, please mute yourself.
Yes, Anjali, madam. Swati, madam, please mute your.
Okay, Golab sir, should I proceed? If there is some technical issue on your side, I can proceed. Is it
Hello.
okay?
Hello.
Yes, madam, go ahead. You are audible.
Yes, ma'am. Thank you. So, good morning, one and all. Today, we also have Dr. Vaishali Tilke ma'am as a resource person for design and analysis of algorithms of assignments of laboratory practice field. So, Dr. Vaishali Tilke ma'am is working as an associate professor in Department of Computer Engineering of Maratha Vidyaprasarek Samajans, College of KBT College of Engineering. So, she is having total 21 years of teaching experience. So, ma'am has published 12 research papers and presented 14 papers in the various conferences. Ma'am won the best paper award in 3 international conferences, ICICC 2017, DSNCR 2020 and ICIDC 2020 in track. So she is also awarded as the best practice paper in the conference by Stranger Nature. Ma'am has worked as the reviewer and the session chair for the different conferences. So I kindly request Dr. Vaishali Tirke ma'am to start with the session. Over to you, ma'am.
Okay. Thank you, ma'am. Okay, I have played my slideshow. I hope it is visible. Yes, madam, slideshow is visible.
Yes, madam.
Okay,
Yes,
thank
ma'am.
you, sir. Thank you, sir. So first of all, good, good morning to all. I, Dr. Vaishali Tidke, want to thank the organizers for giving me the opportunity. Okay, so today we are gathered here for the faculty orientation program of laboratory practice 3. We have started the first session on the design and analysis of algorithm. For a few assignments are already covered by Chobe sir. The remaining assignments I am going to cover. Okay. So these are the assignments, compulsory assignments. Any 5 of these can be done and one mini project can be done out of this. So let us start with the next assignment. There is one assignment that is NQueen's algorithm you have to implement using the backtracking. Okay, so what is the NQueen's algorithm? So NQueen's algorithm is nothing but you are having, say for example, the board of say 4 by 4, and as you have to place the queens, so because the board is of size 4 by 4, so you can place the queen here with the uh, condition that they should not attack each other. So they should not attack each other means what? You should have the 4 queens placed so that they should not be in the same row like this, or they should not be in the same column, or they should not be in the same diagonal. So for example, if your chess is 4 by 4, then you can start the putting the first queen here. Then if first queen is placed here, then now you can put the queen anywhere, but now because we are doing programming, we will have the assumption. The assumption will be that queen 1 is always placed in row 1, queen 2 will be always placed in row 2, queen 3 will be always placed in row 3, and queen 4 is always placed in row 4. Now what we have to decide is only the column. As there are 4 columns, we have to decide what should be the column for row 1, that is 1 out of 1, 2, 3, 4. What should be the column for 2 and so on. So if queen 1 is placed at this first location, that is in the first row, first column, then definitely now we will test for the 2. So we will try to place the 2 here because it is in the same column, you cannot put here. Then similarly it is here, so you cannot put it here because it will be in the same diagonal. So we have put it here. Okay. Now, if 2 is placed here, then we will try to place 3. You will try to place 3 here. You cannot put because it will be in the same column as 1. So let us put it here, for example. But in that case, when 3 is placed, you can test for these all the 4 positions for fourth queen, but it will be in the same row as in this one. Sorry, it will be in the same row. So what you will do? You cannot put it anywhere. So you will backtrack, and then the queen which was placed here, now it will be placed in the second column instead of first column. Okay. So let us understand this by running the program. Okay, is the font okay, or should I zoom it? Is the terminal visible?
Yes, ma'am. It's fine.
Okay. Okay, just a minute. Let us slightly zoom it. Okay, yes. This is the program for 4 queens. Okay. Uh, so you have to specify what is the size of the board here as the option on the command line. And then you can see here there are two solutions possible. Okay, this is the first solution. This is the another solution. Now, if you print it step by step, then also you can understand. So I have modified it slightly to display the output step by step. So as you can see here, so we have given the 4 as the input. So size of the board will be the 4 by 4. Now we are having 4 different rows, 0, 1 and 2, 3. So first we will start by putting queen 1 in the row 0. So here K will be our row. Now in the row 0, we will start with column 0. And because it is the first queen, this position 0, 0 is found optional. Now initially all the queens are shown here because by default 0 is the position. So this first queen is placed at this position. Now we will try to put the second queen. So second queen means we will increment the row because second queen will be placed in the k is equal to 1. Now we are having the options for 0 column, first column, second column and third column. Now the first queen, if you try to put in the 0th column, then it is not consistent because it will be in the same column as in the first queen. So not consistent. Try for the second column. Okay, second row, second column. Again, it is not consistent because it will be diagonal in the diagonal from the first queen. Then you test for the second row and next column. So it is found consistent as shown in our this one, this position of the slides. Okay, so this queen will be placed here. So we have obtained this particular position. Our queen 1 is here and queen 2 is placed here. Now you are going to try for the remaining positions for the queen 3. So what will be done? Again your row is incremented. Earlier it was 1, now it is 2. Again you will try for all the columns 0, 1, 2 and 3. So if you try to put this next queen, that is third queen in the 0th row, it is not consistent because it will be in the same column as the first queen. If you try to put in the first column, then again it is not consistent because it will be here and it will be in the diagonal position from this queen. So again attacking. So if you try to put in the next column, that is second column as well as third column, that is here as well as here, all are attacking. So what will be done? Backtrack, and this queen 2 will be shifted to the last column. Okay, so like this your program will show that for row third queen, this no position is consistent, no position is found. Okay, so the algorithm will backtrack and it will again move to the previous row, that is column 1 and row 2 and column last column where the position is found consistent. As you can see here, the this position is found consistent at it, as it is not attacking. And then if you try to put the next queen here, then this position that is second column is found consistent. So your program will show that here that this queen can be put here. But again, if the first queen is placed here, second queen is placed here, third queen is placed here, Again, if you try to find the position for the fourth queen, this will be attacking by first. This is also attacking. This is also attacking because in the diagonal, and this is also attacking because in the same column. It means you cannot place the fourth queen at any position. So all these positions are shown not consistent, and hence your algorithm will backtrack and it will change the position of the first queen to the second column. So this is the position obtained, this one. And then again now it will check for the second queen, and like this it will move, it will find that this position is the consistent one. So second queen will be placed here, and then for the third queen position will be found. So again this is attacking, so again it is not placed here. So third queen will get this position and the fourth queen will get this position. So like this you can check that there are two solutions, as you can see, and one by one if you want to check how they are placed, then you can also debug. It will show you step by step. So finally if you see, then for the 4 by 4 board, there are two possible solutions. First is this one and second is this one. So definitely this is for trying all the combinations in the syllabus. You have to specify the initial position. So if initial position is specified by this, then the output should be no solution. And if you specify this as the initial position of the first queen, in that case, this should be shown as the output. Again, if you show, if you give as the input, that is this is the size of the first queen, that is this one, then this should be the solution given. And if you give this as the initial position of the queen one, then again there is no solution. This should be the output given. Okay, I have shown you for all the position, all the possible combinations, but you can try for taking the input for the queen's first initial position and then generate this as the output. Okay, so like this you can try for this. So this is the program. I think no need to explain the program. This is the, just in short, I will tell you that here it is checked whether the queens are in the same column or same major diagonal or minor diagonal. Okay. And no, you don't have to check for the row because already you have decided that queen 1 will be in row 1, queen 2 will be row 2. And that is for each queen already you have decided the row. So you don't have to check for the row. And this is the recursive algorithm. So recursively you will start with 4, and then if it is not the fourth queen, if it is fourth queen, then you have obtained the output, you will print it. If it is not the fourth queen, you will try to put this each of this queen at this particular position where k is the row and I is the column. And if it is consistent, that is, if this gives true that it is not in the same row or same column or diagonal, then it will return and the position will be fixed. So like this you can do it. This is the program I have taken from the this link. Okay. So I think many programs are already available. So I have used those available programs and explain you. Then the another one is, okay, so this is the algorithm already you have seen. We are having the quick sort and randomized quick sort as the algorithm. Okay, so this is the sixth assignment, that you have to implement the randomized quick sort algorithm. Okay, so basically what is the quick sort? If you see, okay, So in the quick sort, you are having the input, this as the list, and then you decide what should be the pivot element. So there is the element, either you can take the position randomly, or you can take from the leftmost or rightmost or middle, whatever. And then if this is the pivot element, for example, in that case, you will search for the elements which are uh, lesser and which are uh, uh, larger. So whatever are the smaller elements, they will be shifted on this side and of the pivot, and whatever are the larger elements, they will be shifted on this side, and this pivot will take its correct position. And then the algorithm is applied separately again for this partition and separately for this partition. So this is the quick sort algorithm. Okay. So means if I show you quickly the quick sort algorithm. So if you enter the size of the array, say for example, these are the array elements I will enter. Then step by step it is shown. Say for example, initially you can see here, uh, this is the input, and if you can see that if 65 is taken as the pivot, then all the elements which are lesser than the 65, they have been shifted on the left of 65, and all the elements which are larger than the 65, they are shifted on the right side of the 65, and finally 65 has taken its correct position, it will not move now. And then the partition, this is the partition on which quicksort is applied, this is another partition on which quicksort is applied. Now here generally the pivot we take either always the leftmost element, or always the rightmost element, or always the middle element. But now what is the randomized quicksort? Yes, and this quicksort, simple quicksort algorithm, that will always take the size that O of n log n. But if you are going to consider the randomized quicksort, then in the randomized quicksort, what is done? The pivot element is selected randomly. That is the important case. Okay, pivot element is selected randomly, and then depending on that element position of that pivot element, the remaining elements which are less than the pivot, they are shifted to say set L1. All the elements which are greater than the pivot element X, they are shifted to second set
तेवढंच
L2,
काम करा तुम्ही
and
करणं जरा ठेवलं.
the list L1, that is quicksort is applied on list L1, and quicksort is applied on list L2 until all the list is uh, sorted. So you will select this algorithm randomly, pivot element randomly, all the elements which are less than the pivot shifted to L1, all the elements greater than the pivot shifted to L2, and quicksort you will apply to pivot, quicksort you will apply to set L1 and L2. Means if we check the program, Let me run it. So again, you have to enter the elements. So let us enter the elements. So here, as you can see, whatever is the element selected as pivot randomly, that is printed here. So this is your actual input, and you can see it is not sorted. So randomly one element is selected as pivot. Say initially 50 is selected as the pivot element. So when 50 is selected as the pivot element, then you can see here after applying the quick sort algorithm, the 50 has taken this position, and that is the correct position. It will not change now. And the element which are less than 50, they are shifted on the left side, and the elements which are greater than 50, they are shifted on the right side of the 50. Now, because this is the single one, the algorithm will run on it, but will not change because it is the only one. And next time the element 60 is selected as the pivot element, definitely this is the only part of the array that will be considered as the input with the pivot 60. Now you can see here less than 60 is only 55. So this 55 element is shifted here, and all the elements which are greater than 60, they are shifted on the right side. Again, the previous part is already sorted. So on this partition, pivot is selected. Now pivot is 75, but you can see here 75 is the first element, and it is only the first one, so there will be no change. So nothing is printed as output. Then again on the same, again pivot is selected. So pivot is 70 selected. So in this part, less than 70 elements, that is this one, it shifted here, greater than 70 are shifted here, and like this it will work continuously. And if there is no change, then as it is the elements are printed. If there is the change, then again pivot is selected, say 90, and finally 90 has taken its correct position, and this is the final output which is sorted as you can obtain. Okay, so as this is randomized quick sort, uh, the only change here is that in the normal quick sort, the position of the pivot is fixed, that is either left always, or rightmost always, or middle always. But in the randomized quick sort, what is going to change is every time you are going to randomly select the pivot element. This is the change in the randomized quick sort and the normal quick sort algorithm. And because you are applying every time, depending on the pivot, the maximum two partitions are created. So there is no change in the time complexity as in the simple quick sort. Then another algorithm is the 0-1 knapsack problem using dynamic programming. So very shortly I will explain you this, and then again we will see the program. So here you can see that what is 0-1 knapsack problem. You are having this knapsack with the n objects. You have to put the n objects in the knapsack such that the weight will not exceed this capacity m, but we want to earn the maximum profit. But the condition is that either the whole object should be selected, that is xi will be 1 if xi the object is selected, and it will be 0 if ith object is not selected. That's why it is called as 0 1 knapsack. Okay, so how the program works? uh, it works on the dominance rule. That is, the operation merging and purging is done each time. That is, one by one object will be selected and the objects are added in the knapsack. And every time you add the object in the knapsack, you will check uh, whether you will check for the dominance rule. That is, if the profit of the first object is less than the profit of the second, but the weight of the first is greater than the second object, then the first object will be discarded. And also after adding the object, total weight is exceeding capacity, that is also discarded. Means, for example, this is the example, say you are having 3 as the objects and you are having these their weights, that is 2 3 4, and you are having profits 1 to 5 and say capacity is 6. So initially there is no weight in the knapsack, so 0 0 is there, 0 is the profit, 0 is the weight. You will try to add the first object whose weight is 1 and sorry, whose weight is 2 and profit is 1. So pair 1 2 is added to this, so you are having this one. Then these two sets are merged and means it is assumed that the object is added in the knapsack. Now similarly second object is added, then this is the result, then third object is added, then this is the result. Now finally these are the this is the resulting set, and then these are extra pairs which are generated, but these are not shown here, they are directly removed because the total weight, that is this one, is greater than the capacity. And then we will try to find out which objects are added, and we will find that the first and last object is added, giving us the total profit 1 plus 5, that is 6. So for the same thing, let us see the how the program is written and how it is generated. So if you run the program, again we will give same input, that is 3 objects, weights are 2 3 4, and the profits are 1 to 5, and the total weight is 6. Then we are getting the same thing, that is the total profit is 6, and the as shown here 101 means first and last object is selected, that is first and third. So if you see, then again I have taken this program from this link. Here you are going to accept the number of elements, weights, their profits, total capacity, and because this is the knapsack, every time you are going to add the object, and you will after adding the object you will select the object. You will check whether without adding the current object what is the profit and weight, and after adding the current object what is the weight and profit obtained, and whatever is maximum that will be selected. So this is the recursive algorithm, so you can go through it. Okay, so like this you can implement the dynamic programming for implementing the 0 1 knapsack algorithm. Here if you debug the program and insert the output statements, then you can see step by step result also. So let us move for the next one. Okay. Other than this, there are the problems. I have not included it here, but still I will just discuss it. That is regarding the mini project. So as you can see here that in the mini project, there is the mini project based on the matrix multiplication. So if you see the matrix multiplication, then we have seen that matrix multiplication can be performed using the formula, that is, say if you are having a n by n, b n by n matrix, then each element of C matrix Cij can be obtained by Cij is equal to Cij plus Aik into Bkj. Okay. So what this means? Uh, you will, if you are having this matrix having the elements, say 1, 2, 3, 4, 5, 6, and so on. This is the another matrix having, say again, of size 3 by 3. Definitely result is going to of size 3 by 3. Now here, when this Cij, this value is calculated, then two for loops are executed. For I is equal to 1 to n, j is equal to 1 to n, and third one is k is equal to 1 to n. So you are going to require O of n square time using simple, that is this formula. Now, because we want to implement multi-threaded matrix multiplication, what we can do? So there are various options. One option is that as you have to calculate 3 by 3, that is if it is multiplication of n by n, then n by n values you are going to require, you want to calculate. So first option is you can use n threads. So one thread for each element, and where this thread which is going to calculate Cij, that is C00, is going to calculate for C00. Another thread will calculate this one. Another thread will calculate this. So parallelly you can call 9 threads for calculating 9 elements, where ij will be the parameter that will tell that particular thread that it has to calculate Cij. If ij is 00, then that thread is going to calculate the Cij, that is C00. If it is say 01, then that thread is going to calculate this value 0 through first column. Now definitely you will compare the time required. You can use the system time to find out it, and you can compare at the end. So n threads can be there. Second option. Second option is that instead of using 9 threads, what I can do, I will use one thread for this row. That is, one thread is going to calculate all the elements in the first row. Then another second thread is going to calculate all the elements in the second row. Then third thread is going to calculate all the 3 elements in the third row. So now number of threads is decreased from 9 to 3. But each thread is going to calculate all the elements in each row. Now here definitely the time required will be less than 9 more than 9 threads, but it will be less than the simple multi-threading algorithm. So you can have this option, one thread for each row. Or I can have another option also. What is the third option? Third option is that first thread will calculate all the elements in the first column. Second thread will calculate all the elements in the second column. Third thread is going to calculate all the elements in the third column. So Again, the time required will be similar to that as the 3 threads per row or 3 threads per column. So like this, you have to do. So in this mini project, what is expected? It is expected that students implement this simple algorithm for matrix multiplication. Then students also implement the multi-threading matrix multiplication. Means threads can be created. 9 threads can be created for 9 elements if it is 3 by 3 matrix, or you can create 3 threads, 1 thread per row or 1 thread per column, and compare the time required for each of the algorithm. Okay, so this is nothing but the multi-threaded matrix multiplication. So this is expected in the mini project of multi-threaded matrix multiplication. Then there is the another uh, mini project, that is the merge sort. Okay, so again multi-threaded merge sort. So simple merge sort everybody knows. So simple merge sort is nothing but you are having the list, you divide it into two parts, and each part is separately handled. So again for this, you will divide it into two halves, and then again you will separately merge it, apply merge sort on each partition. Finally, when it will be only each partition will be of say single element, then now you will start for merging, and then finally you will get the partitions. Say for example, this will be the partition which is sorted. This is another partition which is sorted, and then again you will one by one merge, and then finally you will get the elements or the list of elements which are completely sorted. So this is the simple merge sort everybody knows. Again, the time required for this is O of n log n, if it is the size of the list is n. Now how you can do multi-threaded merge sort? So again, as I said that if this is the list, you partition this into two halves. This is separately sorted using merge sort. This is separately sorted. Now you can create one thread which is going to partition this, and another thread which will take care of only this partition. You can continue the remaining using only two threads, or if you want you can also create one separate thread per partition, but using only two threads it will be quite simple. So definitely these both the threads are going to work simultaneously, and definitely the time required is still same, but because they are going to do it parallelly, so the if you compare the execution time, then the time required to run the algorithm will be lesser than the simple merge sort. So this is nothing but the multi-threading merge sort. So definitely there are different ways to do to implement the multi-threading, maybe in Java or Linux or Python. Uh, Different options are there. So I hope it is clear. So it is expected that the students will implement simple merge sorts, students will implement multi-threaded merge sort, and they are going to compare the time required. Then another one more is there, Rabin carb and string matching algorithms. So I think it is already covered in the DA. Uh, Chobe sir has covered it nicely. So I will not take it because already those algorithms are available. But I will slightly discuss the last one, that is the approximation of TSP. Okay. So one assignment is there, that is approximation of TSP. That is traveling salesperson problem. So actual traveling salesperson problem is everybody knows. Slightly in short, I will explain approximation algorithm for TSP. So what is the traveling salesperson problem? You have to find out the minimum cost tour. That is nothing but the traveling salesperson problem. Okay. So if it is approximation algorithm, then what is approximation algorithm? It gives you approximate solution, means it is not the optimal solution, but it is near to the exact optimal solution. That is called as the approximation algorithm. And if you are talking about solving the traveling salesperson problem by using approximation algorithm, then this traveling salesperson problem takes the graph G as the input, where V is the vertices, set of vertices is the set of edges, and that edges represent distance between cities, and uh, each edge is associated the cost Cij, that is it connects the I and j city, ith and jth city. So what is the traveling salesperson problem? You can say that you have to find a Hamiltonian cycle with the minimum cost. So Hamiltonian cycle means you have to, if you start from vertex 1, you have to come back to vertex 1, covering all the remaining vertices exactly, visiting all the remaining vertices exactly once. So you have to find the Hamiltonian cycle with the minimum cost, starting and ending with the vertex 1. So how approximation algorithm for TSP will work? You will start with root 1, root as the node 1. You will find the minimum spanning tree with root node as the 1. Find the pre-order visit for that minimum spanning tree. And meanwhile, you find out the Hamiltonian cycle, and you have to apply the triangle inequality also. Okay. So how you can do it? I will quickly show. That is, for example, suppose let us consider the example. Okay, so let us take, you are having this as the graph, and you have to solve using TSP approximation algorithm. So if you start with, say, vertex 1. Now I'm not going to take the actual program, because everybody knows how to find the minimum spanning tree. Many programs are already available. You can search for them, and how to perform pre-order visit, that also everybody knows. So starting with the root node 1, you have to construct the minimum spanning tree. So if you see this, 1 and 2 is the next smallest one. So I will add this. Okay, I will add this node 1, sorry, node 2, whose distance is 4 from 1. Then if you observe all the nodes connected to 1 and 2, the next smallest is this node 5, having this node 8. You have to observe only one nodes connected to 1 and 2, as it is minimum spanning tree. So this is the node 5 with the distance 8. I will add here. Then next connected to 1, 2 and 5, these are visited. See the all the unvisited vertices connected to 1, 2 and 5. Then you can see here this node 3, which is connected to 5, having minimum cost 5 is there. So I will add here node 3 with the cost 5. Then 1, 2, 5 and 3 are the visited vertices, only unvisited are 4 and 6. So next smallest one will be the, say, node 4 with the cost this one 6, and only remaining is now the node 6. So node 6 is connected to this 4, and the cost for 4 to 6 is 16. So this is the first step to find the to solve the TSP using approximation algorithm. Starting with root node 1, you will obtain this minimum spanning tree. Now, after obtaining minimum spanning tree, if you add this, then 4 plus 8 plus 5 plus 6 plus 16, it is 39. But what we want is a Hamiltonian cycle. This is not, nowhere there is a cycle. So what you can do, you can find out that is start with 1, come to 2. From 2, you have to go back to 1. There is no other option. Visit 5, visit 3, visit 5, visit 4, visit 6. From 6, there is no other option. You have to go to 4, 5, 1. So this is the cycle, Hamiltonian cycle you will obtain. So what you will do, 4, come back. So again 4 plus 4 plus 8 plus 5 plus 5 plus 6 plus 16 plus 16 plus 6 plus 8. This is the total addition. But now here we want to obtain minimum spanning tree. And the cost after from that minimum spanning tree, minimum smallest cycle, that is the we want to obtain. So here you can see that node 1 is revisited. So what you can do, we will eliminate this revisited nodes. So how we can eliminate? From 1 to 2 we will go, but we will not go to 1. Here you will apply the triangle inequality. So triangle inequality say that 1, 2, 5, if 2, 5 are already connected, then the distance between 2 to 5 is less than distance of 2 to 1 plus 1 to n. So this 2 to 1 and 1 to 5 is replaced with this. So this 2 to 5, they are connected with this distance 10. So I will insert this age. I will remove this 2 to 1 and 1 to 8. I will insert 1 to 10. Similarly, this from 3 to 5 and 5 to 4 you are going, that is 5 you are revisiting. Instead of this, remove 3 to 5 and 5 to 4 and add this 3 to 4. So 3 to 4 is nothing but 10. So this is added. So you can see here 8 plus 4, 12 is replaced by 10. 6 plus 5, 11. Now that is replaced by smaller, that is distance 10. Similarly, from 4 you are going to 6, but 6 to 4. So 4 is revisited. So why not 4 to 6? Why not directly go to 6 to 5? So 6 to 5 is having the distance 19. So you can see that 6 plus 16, that is 22, is larger than 19. So 22 is replaced by the age 19. And now again, uh, you are going to 6 to 5 and 5 to 1. So 5 is revisited. So instead of that, again you can remove this 19 and you can replace it by 6 to 1. That is 6 to 1 is 26. So if you add 19 plus 8, it is smaller, I think, and you will get the this one. So finally solution will be 1, 2, 5, 3, 4, this 6 and directly to 1. So this is going to give you the solution for TSP approximation. So this is different than the exact TSP problem. I hope all of you have understood. So here I have not taken the program because the program required is obtaining the minimum spanning tree, and after that pre-visit order of the minimum spanning tree. All this is required, and after that simple additions and subtractions are there using the triangle inequality. So I hope it is clear. So this is over from my side. In case you are having some problem, please ask.
Yes, participants can ask the questions if they have.
Yeah. Hello, ma'am. Hello, Vaishali, ma'am.
Yes, ma'am. Please proceed.
Yeah. Uh, for the TSP with approximation, one question in mind. The example which we have handled was the complete graph, in which we were having the age from the last node 6 node to very first node, that is 1, right? But is the case like if there is no age present in the graph from last node to very first node, okay, then what to do in that case?
If there is no?
If there is no age from the very last node to very first node in the graph,
then the previous one will remain. You will not replace it. In case there is the edge, then only you are going to apply the triangle inequality. What the triangle inequality says that the two sides of the triangle, they are definitely having the larger, their addition is larger than the third side. Means
Right.
you avoid those two edges, traveling by those two edges, you go through the third edge. That is triangle inequality. So this is applicable only if these three nodes are connected. Otherwise, you cannot apply it.
Yeah, yeah,
Okay.
and yeah. I got that concept. Like, only my question was if such a graph is present. Like, see, here we are starting from the first node by default,
Yes.
and it may possible. It may suppose we are unlucky, then it may possible that we don't have the edge from the very last node to the start one. Then we stuck here.
No, will not stuck because somewhere the nodes are connected. Because while obtaining the minimum spanning tree, you are considering only those nodes are which are connected. Those edges you are reflecting will be reflected in your answer. So I think we will not stuck.
Like whatever the graph we have selected. For example, can we go for that graph?
Okay, just a minute.
Yeah. It is just for this students' questions.
Yes, yes, no problem. Yes, yes, no problem.
Yeah. So here in this case, suppose I don't have the age from 6 to 1.
Okay.
And in the tree, in the MST, our last node, which is at the bottommost level, was 6, which was the last one
Yes,
to visit.
yes, yes.
So
It
from
was
6
one
to 1,
year.
yeah. So if there is no path from 6 to 1, then what to do?
That's what I am saying. Because see, what is triangle inequality? Triangle inequality you can apply only if there are the edges. If there are no means these three nodes are not connected to each other, then you will not apply triangle inequality.
Okay. Then
So
in that
that
case,
will
I should
not
go
come
for a
into
parent
picture.
of
The
6.
case will not come into picture itself.
Okay.
Okay. It is important that these two are connected with each other. If they are not connected, you cannot apply the triangle inequality.
Okay.
Okay.
Like if there is no path from 6 to 1, then I should think about
Yes,
its
yes.
path.
Yes, yes. Then there is no option. You have to revisit that node. Triangle inequality will not be applicable.
Okay. Fine.
I have to revisit that node. I cannot
Yes.
avoid.
Yes. And then in
Okay.
Hamiltonian cycle, is it compulsory that every node should come only a single time during path?
Yes, yes. What is Hamiltonian cycle? There is one start. Say for example, one is the starting vertex. Then my end
And then,
vertex should be one, and I have to cover all the remaining vertices. I have to visit all the remaining vertices exactly once. That is the Hamiltonian cycle.
right. So if from 6, if I'm visiting the parent node, that will be
Hmm.
repetition, and we can say that it is
Not
already
allowed.
visited. It
Yes, you
is
can, not allowed.
not
From
allowed.
1 to 6, if you are going from 1 to 6, you cannot go back to 1. You have to go to the another node only. Remaining unvisited vertices, you have to go.
Okay.
Okay.
Yeah. Fine. Thank you, ma'am.
Okay.
Any questions from participants?
Yes, I think Sarika Power ma'am has asked, can we use Python for implementation? Yes, ma'am. It is mentioned in the syllabus. You can use anything, C, C++, Java, Python, as per the choice of yours. Whatever students find it easy for them, they can prefer. So we have not kept the choice of the algorithm, choice of the language fixed.
Okay. So, if you have queries, you can ask in chat box also. You can put your queries in chat box. Okay. So,
Okay. And one more thing, again, I will like to mention that for mini projects, you can have 2 or 3 students, but not more than 3. And as usual, mini projects will not be asked in the exam, as this is going to have the exam. Only the assignments will be asked in the exam. Okay.
That is, we have to make a group of 2 to 3 students for every batch, and different problem statements should be provided as the mini project statements, right?
Yeah. It is better to cover different mini projects in different batches so that
Yeah.
students can share with each other.
Yes.
Okay.
Yes, ma'am. Tidke ma'am,
Yes.
should we
Okay.
conclude?
Before concluding, I would like to thank the organizer